finish this. And some of this will hopefully make better sense as we go and talk more about geologic structures, but it gives you a framework in which to think about how the processes that are to give rise to various geologic structures, fault folds and fabrics. So the basic topic here is what would be referred to as deformation mechanisms and microstructures, but it's kind of back and forth in scale from micro to macro. In this discussion, I'm going to kind of start at closer to experience of rock deformation, which is the shallow crust of how rocks behave in their surface environment, and we'll work our way down into the crust or into the lithosphere and talk about other deformation mechanisms that occur as you go down into deeper levels within the Earth. So in the shallow crust, the rule is the development of brittle deformation. And what do I mean by brittle deformation? What actually happens when for a material to behave what you would call brittly? Physically, what happens to the material?
It starts to crumble.
Breaks. Yeah, you make a discontinuity within the material. And so in a sense that I've used the word discontinuum mechanics to describe faulting because you're making little ones out of big ones, basically. Material starts out in a rock body is continuous from some other process that formed it. When it is subjected to brittle deformation, you form discontinuities within the material. The normal way that occurs is along faults or along motion during slip along faults. But tends to be a layering. And we'll come back to this figure a couple times during this class. But if you think about that, there's processes that occur along a fault that's a function of depth that is related to the processes that are affected along that system, such that in the shallow, personal experience tells you how rocks behave, right? They're very brittle and they break and whatever, and there are features on the surface of the Earth we'll talk about later in describing faults and recognizing active deformation on the Earth's surface. But as you go down into the crust, experience from naturally deformed rocks, I said it right, indicates that you can see a general variation of material behavior as you go from shallow, this is supposed to say incoherent cataclazite. So cataclazite is a word used for fault rocks. Cata meaning deep and clazite meaning broken, so deep broken rock. And the general word for fault rocks or materials that are formed along a fault zone are cataclazite. So there's typically has a tendency to be with greater depth, what's called here cohesive cataclazites. But another way of looking at that is those rocks are often highly subjected to hydrothermal alteration. You're probably introduced to that term in mineralogy. Mm-hmm. But what that really means is vast amounts of water flux through the materials and change their characteristics. So they've been incredibly hydrothermally altered. Geologists have known that for centuries. That's commonly exploited in mineral deposits. So many faults are mineralized because of the fluids that move through the material and produce mineral deposits. But as you go to deeper levels, cataclastic rocks transition down into shear zone rocks, which are features that are often referred to as mylonites and often mistakenly called fault rocks. They're not really fault rocks, and I'll talk about that as we go along. So let's work our way through that succession and talk about some of the processes that are operating. So we'll start with the brittle field and work our way down into those deeper levels in the Earth's crust. A cataclastic fabric is just schematically illustrated here. I just make little ones out of big ones. This is natural experience. You grind up something, you break it into littler and littler fragments, and that's kind of what the process is at the microscale for brittle deformation, is you just make little ones out of big ones and you grind down the material. Cataclazites are not something most people love. They got to be the ugliest rocks anywhere. They are typically grungy green and brown because of hydrothermal alteration. So waters move through the material. They're already they can be powdered by deformation, and then they get altered by hydrothermal alteration, and they just get this kind of ugly green ground up junk, right? And that's what they look like typically in thin section. I mean, it's hard, sometimes they look just like a sandstone, hence the word cataclazite, because they're just comprised of fragments in a matrix. And the dimensions of this we'll talk about more when we talk about faults. that are typically limited to zones of a narrow zone in which the damage occurs along the fault zone. These will transition downward into rocks that show mixed behavior, and I'll come back to that too, where some minerals can behave brittly while other materials start to flow. And so there's a transition that occurs that's naturally seen in naturally deformed rocks, and we'll come back to that too. For a long time, people have talked about deformation mechanisms at the grain scale. And I'm not even going to bother you with that in part, because it's sort of useless for geologists in the sense, yes, it does tell you something about the process at the small scale, but the biggest factor in earth materials is that earth materials are so brittle that what's causing most of the mechanical damage is the material just fractures into fragments by extensional fractures and makes little fragments. But the real effect, or the biggest feature of note for geology, really in general, is at a larger scale than at the grain scale. So we can talk about broken windshields and all that kind of stuff, but let's not bother with it. And instead, let's talk about something else, which is embarrassing to admit for how long it took geologists to realize that a very well-known process, earthquakes, are at the heart of what you see at geologic scale of the rocks you see, the deformed rocks and fault zones. That's also related to an issue we talked about last time, which is Byerly's law, or this observation that was related to the constant angle between fault planes, the so-called conjugate angle, and the inference that most geologic materials have fairly constant frictional properties. Those two together have important implications about how fault systems work at large scale. And the first thing we want to talk about in this context is what I might refer to there as the macroscopic behavior of faults, or a deformation mechanism at large scale. This isn't typically at grain scale. This is at meters to thousands of hundreds of meters, or kilometers in scale. And what it's related to is related to, well, let's talk about a windshield effect first for a moment. You get a broken windshield, right? One of the things that often happens is on a cold day, the fractures will propagate across the windshield, right? That's because of thermal stresses and concentration of stress at the tip of the fracture. And you can show that theoretically. But the important point is that there's a magnification of stress effect at the tip of the fracture. That type of fracture in fracture mechanics, that type of fracture, the windshield type fracture, is what's called a mode 1 fracture, which means that kinematically the fracture forms by an opening in the fracture. And so it propagates by the concentration of stresses at the tip, make the stresses go tensile. And so the fracture propagates at that fracture tip, even under very low stresses. This turns out to be mostly operating in earth materials at grain scale. At larger scale, the effect is more characterized by these two other modes, which are shear modes and the motion of materials along or the motion of rocks in shear mode, where the motion along the fracture is the faulting mode. So materials moving, the kinematic mode is to move parallel to the surface. The important part of that, though, is that process is also subject to stress concentration. In the simplest one is this one, which is called mode 3 failure. There are analogs of this at crystal scale, and we'll talk about shortly. It's described here something about dislocations we'll talk about in a minute. But this one's, in many respects, easiest to see. If a fracture is forming within a material, it doesn't instantaneously fill the world, right? So as a fracture forms, or as a discontinuity forms, it propagates, just like the fracture on the windshield. But when it's in shear mode, the stress concentration is different depending on where you are relative to the sliding motion. And the tearing mode is the simplest one to see, because as the material starts to move your hands, you can see that there's a scissoring effect. It's going to tear material in advance of the propagating fracture. That concentration of stress in mode 3 makes the fracture propagate in this direction. But by the same token, if you're in the advanced part of the system, there's a pileup. So material is moving in this direction. There's too much mass, so to speak, on the one side. It's a relative thing, so it doesn't matter. But there's a tip effect where there's a stress concentration at that tip. And that also allows it to propagate forward and backwards and sideways. So what happens is you can initiate slip at a point within a material, and it spreads out by propagation. And it can do that at much lower energy than it would do by just fracturing all at once. Now there's a common analogy that's given to this, and it also applies to crystals. That's the least energy system for forming and moving, or even just moving a fracture. And the analogy that's always given is the gorilla and a piano moving a piano analogy. You have a piano sitting on a rug. The gorilla approach would be grab the rug and yank it out from underneath, right? Well, that kind of takes a fair amount of energy, right? There's an easier way to do it. If you lift up one leg of the piano, ruck it underneath, move the other side, pick up the other side, ruck it out. Suddenly you move the rug out from underneath the piano, or I guess you're moving the rug, not the piano. Sorry, I didn't say moving the piano, but removing the rug from underneath the piano. That second method is a lot lower energy. That's the exact analogy that occurs in materials that are undergoing slip in these kinds of modes, where it takes much lower energy to propagate the fracture that way because of the stress concentrations that occur as the material expands outwards and makes a net motion along through the material, or make a fracture that propagates through the material. There are small-scale structures that are interpreted as manifestations of this particular process that you can see on many joint surfaces where there's a natural fracture in the rock. And they attest to this kind of process of the formation, a dynamic fracturing process of this sort. They're called plumose structure. This is from your book, I think. And the way they're interpreted is that the fracture starts here and propagates outwards, and it loses energy outwards, and it dies out into a series of smaller scale features. But if you have this cascading one after another, where things get bigger and bigger and bigger, and you can eventually make a fault, for example. Hopefully we'll be able to see something like this on field trips. There's a whole bunch of details of this that, unless you're into fracture mechanics, you wouldn't necessarily care about. But the key point is that there's natural evidence that's interpreted in this context of this sort of dynamic or stress concentration at mesoscale, at least. Do you have a question?
Did you say plumo structure?
Plumose, P-L, like plumose, P-P-L-U-M-O-S-E. And there are a bunch of other things that are detailed in this. Your book has some descriptions of them if you want to go through them. The author of your book is sort of into this stuff, and he has more than a lot of people have in that. The key for us as geologists is that process scales upward to a well-known process, which is basically seismic slip. There's a complete analogy to that. But that process is also related to the two different classes of material behavior that have been recognized by geophysical studies, especially earthquake studies and geodetic studies of active faults. And those two classes of behavior are referred to as seismic slip and creep. Those two, if you're aware of those, let me go back one again. Well, let's talk about those observations. From both seismology and geodetics, it's known that most faults show one of those types of behavior. In creep behavior, it's like the pictures you've seen of places in California, like the football stadium, I think it's at Berkeley, that has gradually been moving at 2 or 3 centimeters per year. But they don't have earthquakes. It just gradually creeps. You have to fix a road once in a while, and you just kind of keep rebuilding the road and moving fences around. But the more common type of behavior is what's the one that nobody wants to have happen, which is seismic slip, which is, and it's the more common behavior, is sudden motion. So episodic slip sits there for decades or thousands of years and then suddenly slips. More recently, there's even a third type of behavior that is still not particularly well understood. there's a whole class of motion that's often referred to as slow earthquakes, have been known for some time, but it's related to a feature that's now often referred to as episodic tremor. Any of you know of this or have heard of this? It's a very strange phenomenon. It was first recognized in the Pacific Northwest. Normally you think of faults as locked, waiting to, locked and loaded, so to speak, ready to go. But what occurs in episodic tremor is at time scales of months to years, the fault will behave like it's locked. And then all of a sudden, for periods of 2 to 4 to 6 weeks, maybe 2 to 3 months even, there's an accelerated slip that's recorded only, that you can only see by geodetics and very low frequency seismic emanations. And what's occurring is all this, it's part of the seismic zone is slipping. And there's a lot of theories around, but nobody quite knows what's going on. But it counts for a lot of slip on a lot of these margins. It may be triggering other things, it's not clear, but it's out there, you can read about it.
Now, when you say the Northwest, where do you mean?
The subduction zone from Northern California to Vancouver Island.
Okay.
Cascadia.
Okay.
Are you talking in Washington as well, because that's where there's a lot of.
Yeah.
Yes, it was first recognized in Washington.
Okay.
And there's a lot of literature about this, like hundreds of papers written in the
Can
last
you feel it,
10
or is
years.
it just something you see?
You can't feel it at all.
Mm-mm.
It was only recognized with super sensitive instruments that could see it. And, it was always thought there was something. There were slow earthquakes that had been recognized previously by some low seismic emanations, but these are part of that process. And like I said, we don't really understand it, so I won't.
So did they discover this in the pursuit of, say, the geothermal they were doing in the Northwest? Or?
No, it was totally serendipitous.
Huh.
Now it's been seen like 2/3 of the faults, big faults around the world display this.
Has this also been seen in Japan?
Yes. Middle America,
I think
Andes,
I've heard
there's
of
lots of places. Most subduction zones show this to some extent. Anyway, it's there. You can, if I knew the answer, I'd give you more than just a statement that it exists. Beyond that, there's a lot of literature that there seems to be converging on a solution, but I don't want to bias you on what that, because I'm not sure I believe any of them. Beyond that, though, there are two types of behavior that are well known, that have been known for a very long time, and you even know about this, that are directly related to these observations of creep and seismic slip, is two general forms of material behavior and friction. It's long been thought that faults behave as a frictional process. We already did it last time in the discussion of just the general nature of faulting systems has a strong component related to friction. But there are two different kinds of friction, sometimes called stable sliding and stick slip, that have direct analogies to creep and seismic slip respectively. And they are basically related to a physical property. That's a physical property that you're well aware of. The connection occurs at different scales. We already said this, so I don't have to do that. But it's really related to the well-known property that you learned in grade school, which is the relationship between static coefficient of friction and what's called kinetic coefficient of friction. Do you remember that distinction? What was the difference?
One you have to overcome in order to become.
Make it move, right?
And then the one that you actually have.
When you're just sliding it, right? What the strength of sliding it. What's the usual observation? For most,
Static coefficient is higher than the kinetic.
correct. And that gives rise, that's exactly why earthquake slip is more common than creep, because that's the way most materials behave. They have a breakdown stress, that's the static coefficient of friction, that gives rise into a kinetic friction, which is a lower stress, sliding values that are lower friction than the static values. In other words, if a material lacks a distinct static coefficient of friction, so that the kinetic coefficient is, for all intents and purposes, the static one, the material slides stably, or you have creep behavior. If you have static much greater than the kinetic friction, you have stick slip and you have earthquakes. There's a place, you do this all the time and you don't think about it. I always wanted to call click and clack on this one, right? Your car brakes rely on this, right? If your car brakes, the brake materials that are used on your car brakes did not have this behavior of stable sliding behavior, it would be really annoying. Because every time you'd step on the brakes, it goes, kind of like ABS brakes, right? But it's not the same thing. It would really literally be like micro earthquakes occurring as the material stick, slip, slip, stick, slip, slip. And that's why I was always going to call. I had a car that did that once, and I was always going to call click and clack and tell them they could solve the problems of earthquake prediction if they could tell me why I did this. But I never got around to calling. But fundamentally, that's a physical process, right? And so I never did know why my car did that, but it did do that. It was under certain weather conditions, so that made it even weirder. But how does this actually work? Or what's the physical process that gives rise to this? That also is relatively well known. There's a well-known theory for this process of rock friction that has to do with concepts of what are called asperities and breakdown stresses that occur during stick slip. And what that, the way it's commonly modeled, we talked about these kind of little diagrams, is earthquake slip is modeled like this, where you have a spring attached to a slider. And so as you pull on the spring, if you pull this at constant velocity, you increase the stress until the material slips. And you drop, you release the energy of the spring, then you start accumulating, drop, and so forth. That's the classic seismic slip cycle that occurs where you get this breakdown effect. The explanation that's generally given to this particular process is that materials typically have a characteristic where the sliding surface, especially once it's formed, this is generally in reference to once a fracture is already formed, the surface is never perfect. And there are irregularities along the surface that scale through a wide variety of scales, from tiny, tiny microscopic specks to larger contact positions. And the friction is such that it has to break through those various barriers in different ways. It has to be broken first before you can actually make the surface start to slide. So that, here's just another illustration of that. You could have just a thumb sticking into the surface that has to physically gouge out the material underneath it. That has to be overcome, or you could break through that. One way to do that is to break through that rather than have it gouging along the surface to release the energy. And that's basically the idea of what's occurring at local scale along a sliding surface. What that looks like sort of as a patch on the surface of a material that wants to slide is that you have strong contact positions that are at various scales along the surface. And what that can do is that the strength of these guys are what really control what's going to allow it to slip. If you can break one of those, then it'll allow it to break, slip, and move. And that's the general theory of stick slip, is if you can make a cascade effect, once you break down the biggest contact asperities, then it can move. And then you go into a kinetic mode that's different than the static mode. Earthquakes also tell us about this process and tell exactly the same kind of story, or the story is at least consistent with that basic theory. And this is another one that's sort of embarrassing that geologists for so long didn't talk to earthquake seismologists and understand that the two are telling the same story from a different perspective. I mean, it wasn't until like the 80s that they ever talked to each other and really talked about this stuff. It is kind of embarrassing, right? But there are two general, a lot of geologists still ignore it, but we won't go there. There are two basic observations that made in seismology that fit well with this kind of general characteristic. The first one is one you might not think about. Whenever they report an earthquake, what's the first thing they give you, right? A location,
Magnitude.
right? On the other hand, think about an earthquake like the Japanese earthquake or the Indonesian earthquake, these gigantic earthquakes, right?
Mm-hmm.
The area that's affected by the earthquake might be 1,000 kilometers long, yet they talk about the location of the earthquake, right?
The epicenter.
It's like, why would there be a location, right? Why isn't it here, not a point, right? You may not have thought of that before, right? But that actually tells you something very profound about the nature of the seismic source. That the nature of the seismic source, that source is like that little diagram I showed of the rupture propagation effect. It means that the rupture begins at a spot. It cascades outward, and the rupture propagates dynamically by stress concentrations that lie at the fracture tips. So as they propagate forward, the surface moves with the distance that has the energy enough to move to overcome the kinetic friction once it overcomes that cascade effect. But it moves primarily because there's a rupture front that's propagating outward. But the fact that you can locate the earthquake to a point just tells you something about the speed of this process. That the waves that come out of the system, which are the P waves that earthquake seismologists record, have to be much faster than this thing propagated. And that's well known from a lot of different sources. Even observers have seen, it's now basically from modeling these kinds of sources, it's now well known that that rupture propagates at about the propagation of the shear wave. So P waves in the crust might move at 6, 7 kilometers per second, whereas the shear waves move at 3 kilometers per second, something like that. That also might tell you why really big earthquakes last so long, right? If that front is moving at 3 kilometers per second, and it's 1,000 kilometer long rupture, you can do the math, it's going to be a while, right?
6 minutes.
It's like several minutes before the event's over. And in fact, that's what events like Japan or Indonesia were like that. They lasted like 3, 4 minutes, right? And that's why people always say they think the world ending, right? Think about how long that would seem, 3 to 4 minutes when the whole world was shaking and you can hardly stand up, right? But anyway, that's a little off the point. But the big point is that's consistent with this idea of the rupturing of a disparity or a strong spot on the fault breaks and propagates outward, sort of a dynamic rupture. The second observation from seismic studies, or from seismology studies, indicate that most of the energy release in a lot of these earthquakes occurs within the first few seconds of the event, or at least by that I mean most of the energy gets released early on and then it fades. So the rest is sort of a dynamic cascade effect. And that's consistent with this idea of a strong patch or an disparity that has to first break, and once that breaks, the rest is a cascade of just the amount of energy that's available allows it to propagate out to the tips of the rupture. What's also known is it's the same sort of thing, is that it's all by that same sort of modeling. Many seismologists have recognized that a lot of earthquakes are multiple earthquakes in that context, so that the first event triggers another or another. So sometimes there are 2 or 3 that comprise the event to make a really giant event. That's actually what happened in Japan, for example. The Japanese thought that the earthquakes always occurred in the same patches. And they didn't think about the fact that a big one might trigger all the other patches at once, which is what happened. Instead of just having one patch, the whole system went at once. But it's related to the same process. You can see how that cascade effect could easily trigger the next segment. And it's just hard to judge when that's going to happen. Sometimes it occurs days later too, right? Mm-hmm. Sometimes there are 2 great earthquakes in the same place in a week or something like that.
I was in Salt Lake and we had them early one morning, and about an hour later after I was at school, we had another.
That may have been aftershock, which is a slightly different deal, but yeah.
Yeah, it was pretty strong. I mean, we had rumblings in between, but it was like 2 strong ones.
Indonesia was the best illustration of this. When the Great Indonesian earthquake occurred, there have been 3 monster earthquakes after that earthquake. within the last 10 years. And they're thought to have been triggered by just by the slip effect or the stress concentrations of the previous earthquake. Here's just sort of an aside to talk about. This is an interesting historical feature because I said geologists didn't even understand this process. Just thinking this way was actually an illustration of something that solved a paradox, a so-called paradox that occurred, that was described in the 1950s. In fact, I'm old enough that this was still thought to be a problem when I was an undergraduate sitting in a class like yours. It was called the paradox of low-angle thrust faulting. And here's the way the calculation went, and I got the kind of the answer set up here. But the idea was just to do, okay, they knew about already, to some extent, they knew about Byerlee's law. That materials had sort of the same kind of general friction characteristics. So the problem was set up this way. Just take a block, right? Piece of granite. It's this height and this width. And I know the coefficient of friction of this material, and I know the strength of rocks. I can take a rock column that's 10 kilometers thick, say, which is typically what might be the cover on top of a low-angle thrust fault. And I could calculate what would be the stress on the back side of this block that would take to make that block move. And what the calculation showed was that that block couldn't be wider than about 15 to 20 kilometers, or you would exceed the strength of the material and you'd crush the rest of the rock, right? That was the so-called paradox, yet it was well known that there are many, many thrust faults that were essentially flat. They formed when they're essentially flat. That launched a whole generation of studies that talked about fluid pressure as an explanation of this. And that is, in fact, probably part of the actual story, but it's a trivial part of the story, actually. There's a great experiment. I should have done the beer can experiment here. We should try that sometime in the
What is it?
class. Remind me of it sometime and we'll do it.
What is it?
It was a classic fluid pressure experiment. Have you ever had, been at a good illustration is of being in a restaurant and they give you a very cold drink on a very humid day and your glass is sweating away and whatever. It'll almost slide off the table on you. The beer can experiment is done the same. You can determine because you're getting fluid underneath the material, it's producing a fluid pressure. The beer can experiment was done in reference to this problem. Only a geologist would think of this. The first thing you do is you have this beer and you test the beer can and see what the friction, how steep the slope will have to be to slide on, right? Then you sit there and you
Empty the volume a little bit.
Beer, right? And then you put it into chilled in like dry ice or something like that. Flip it upside down. You had to use the old-fashioned pot tops that would come for set it upside down, and then as it warms up, all that air would come rushing out the bottom of the beer can, and you can make it. I swear to God, you can make it slide down a slope of less than a degree, because you're basically producing fluid pressure. It lifts it off, and it can slide down with an apparent low coefficient of friction. And that's what people thought in the 1950s was the solution to the paradox, was that. But it turns out there is no paradox, because the problem is formulated wrong. It's formulated in the context of static friction. The moment you consider a problem in the context of asperities and breaking asperities, this is a lame calculation, because it has no bearing on the problem, because it may actually, the only thing it may tell you something about might be the size of asperities. They have to be broken to make the material slip. But once you go into a dynamic system, the stress concentrations far out magnify any effect of that sort. So you can make the material slip at much lower slip magnitudes. So the result is that so I'll come back. I guess I got my jump here. There's another part of this thrust paradox too, though, that came about that is important to understand. This was also done in the absence of a context of what the real world might be like. And that is that most of the world is not, well, maybe a lot of the world is flat as Kansas, but in mountain areas, which is the area where active faults are moving, it is typically not as flat as Kansas. In fact, when you have stresses and surface slopes, you have a very different scenario that actually relates to this particular problem. I'm not going to do this chalk talk. I can tell you in words. We talked about, well, maybe I can. Remember when we... Remember when we talked about Anderson's theory of faulting? Great. I guess I'll do it. Won't be chalk talk. Yep, there we go. Last time I talked about Anderson's theory of faulting is one of the stresses, sigma 3, was vertical during thrusting.
Mm-hmm.
And so sigma 1 was vertical. And what that said was is that this was sigma v, because sigma v had to be parallel, that had to be perpendicular to the free surface of the Earth, which couldn't withstand the shear stress. And so using more Coulomb failure criteria, we had this prediction that faults would typically dip something like 30 degrees, would be one typical part of that particular problem. Well, one thing that we realized, when it's not flat, sigma v is no longer v either. So if you have a slope, the same kind of symmetry effect has to apply, that the principal stresses need to be, at least in the shallow part, perpendicular to the surface. But if the slope is there, then so are the principal stresses also are inclined. And therein lies the important part of that particular story, because the moment you make a surface slope, you're into the engineer's problem and not the lame problem of sliding a flat block across the surface. And the engineer's problem is this one. When you're on a surface slope, the minimum stress may be sitting in here, the maximum stress is down the hillside. And what that means, what that effectively means, is that instead of having, if this is say a slope of 30 degrees, then all of a sudden your two principal, your values here, I didn't quite have them drawn right. They're drawn right. They're 30 degrees from there and 30 degrees from there. This one suddenly has a very much lower dip than it would if this was tilted back this way without the presence of the surface slope. It would be down in here. And what that means is if you have a surface like this that's underneath this, you can make this slide because of the surface slope. This slides under a different stress state condition.
Mm-hmm.
So now you don't even have the one part of the paradox doesn't even exist, the fact that you shouldn't even have sliding on the surface. You've got maximum resolved shear stress right along that particular surface, just because of the surface slope. Now there's actually more to this in the sense that there's other things that you have to calculate, the elastic stresses and a bunch of things in there that don't really matter. But the basic part of the story has to do with this surface slope aspect and the fact that to move it, then there's a natural, even though the material is compressing in this direction, the stresses are actually inclined because of the surface slope. And this is the engineer's problem, right? This is a big deal if you're looking at slope stability on a surface, because that means you can have surfaces that you don't think necessarily would be a big deal, but if they have the perfectly inclined stresses on those surfaces, then you've got to worry about it and things like that. The bottom line of that is, so this kind of calculation is basically lame, and the real problem is one in which the motion in the thrust problem, at least, is related to a surface basal slope problem, and the fact that the mechanics of the system is such that you're not moving a block that looks like that, you're moving a so-called wedge. And there's a whole theory we'll talk about later in the context of thrust systems that relates to these so-called orogenic wedges. That's exactly what mountain fronts look like in thrust regions or in convergent plate margins. That's exactly what they look like. They are tapered systems where there's a surface slope and a back slope that's the base of the thrust system. And that taper is the more critical thing that's related to the mechanical properties of the material. Now, there's a whole theory that goes with this that is beyond the scope of this class, but I'll just make a statement here to get you a feel for this. There's a theoretical studies that were done 20 years ago or more, that basically relate the shape of this taper, the surface slope and the basal slope, in this case for convergent plate margins, that relate to the strength of the wedge and the frictional properties along the base of the wedge. And this is one of the things that bothered people early on, because this is like, especially something like that, it's like pushing, this stuff's weak, it's like wimpy mud, it's like pushing nothing across the surface. But the analogy that's given to this is like a bulldozer blade. Really, that's the better analogy. Is that as the bulldozer blade pushes out in front of something, it boils up in front and maintains a surface slope, right? It's exactly the same analogy of how this system works. But if that bulldozer is pushing wet cement and not pushing gravel that has no water in it,
Doesn't build
that
up.
taper is very different, right? The wimpy cement is going to push way out in front because just a little bit of surface slope will make it push forward farther along. And the cement makes a good analogy because it's related to the fluids that are in the system. And so what has been shown theoretically is that these systems actually, the taper is related to the amount of fluid pressure that's within the material. So in one sense, the early geologists that talked about the importance of fluid pressure were right, because those kinds of calculations, and this has been borne out by literally drilling holes through the faults in these kinds of systems, that the fluid pressure ratios in these things are on the order of anywhere from 50, 60, 70 to 90% of the fluid pressure. Now, what is that term? I forgot, I should have put this up first, I realize. Now, I'm speaking here instead of looking at it on my screen. The fluid pressure ratio is just the ratio, that pressure lambda is the ratio between hydrostatic pressure, which is just, or hydrostatic pressure is the pressure of the weight of water, and so rho GH is the weight of water, versus lithostatic pressure, which is the fluid pressure of just the weight of the rock times GH, right? The fluid pressure ratio is the total fluid pressure over the lithostatic. So when that's hydrostatic, that value is only about 0.3 or less. But if this value gets large, as this approaches this value, then the fluid pressure is approaching lithostatic. And those values on this back were calculated here, so that implies that you're close to lithostatic pressures, fluid pressures within the material. Yes, sir?
When you're saying you're drilling through that, are you taking from like a geochemical standpoint, the fluid pressure?
No, they actually physically measure.
Okay.
Actually, that's a good illustration of a concept that I probably should have said. This whole business of fluid pressure was also first recognized. It was partly why the whole concept of fluid pressure became important. It was first recognized in petroleum exploration. They found out the hard way, right? The classic one is all the old Hollywood movies, right, of a so-called gusher. That is a total screw-up, right? But those, when people first started drilling oil wells, they realized that many oil reservoirs or any things of that sort were overpressured. Because anytime a well flows spontaneously, it's overpressured. It's artesian flow, basically, right? And the greater that fluid pressure, the greater this ratio is. And what they found early on in the Gulf Coast was that some of those, as they found out, as BP found out, was reminded of, I should say, because they knew it quite well, that in Gulf Coast wells, typically when you hit certain horizons, fluid pressures are very close to 0.9, 0.95 in some of those rocks. And the only way they can get over it, how they figured out how to do it, they just took rho GH. Instead of putting water in the borehole, they used heavy mud. They increased the
Density.
mud weight by adding barite, things like that. That increases the fluid pressure at the bottom of the hole, and the hole won't blow out. And that's how it was first discovered, and that's how they controlled wells, or drilling, scientific drilling too, was you had to have a lot of mud weight.
Like a squishy cap, basically.
Yeah, it's just a fluid, so if you can cap it with the fluid, it won't come roaring out of the hole. But it does illustrate that many natural rocks are under high fluid pressure. And these kinds of things bear that out in terms of these theoretical relationships. And without going into theory, you can just know that, and you can worry about that theory at some later point in your career.
That's what happened at Humboldt, Texas, right?
At where?
Humboldt, at the old RT remember.
Oh, the original
The
blowout.
Original blowout
Correct.
that was so famous would turn into Exxon later, so.
Yeah, that was the first they even knew that was a problem. Because some of the first production they ever made was just pump it, right? But when they had the wells blow out, that was the first they knew they had excess pressure. But some of these are way beyond it, right? Like the deep hole and the BP blowout was a good illustration of that. That was super overpressure material. And we'll talk about some of this a little bit later, but basically the bottom line in this context is that lame little statement of the little block sliding, the reason it's wrong is, first of all, the stresses they're Andersonian, but they're not Andersonian in the sense that they're vertical. The stresses are inclined, so part of it is purely geometric. But you have a surface slope, basal slope, so the material can slide because of that geometric effect. And the second effect has to do with and that has to do with this, but the second effect has to do with this context of seismic slip versus just sliding. You have that the material can move easier. And then you have fluid pressure, and fluid pressure can aid the process, but it isn't essential. You can still move a fault. All you need to do is have the energy right to do so. Now there are modern day paradoxes that remain that are yet to be resolved that do relate to this issue that aren't quite so lame and have still yet to be resolved. And we'll talk about these more when we talk about this, when we talk about specific fault systems. But one of them is low angle normal faults, and the other are stress measurements on the San Andreas fault, where this in situ stress measurement puts, I'll just draw a picture here, and that'll be the end of today's lecture. And if I can find it. The observation of the San Andreas is if you have the San Andreas fault sitting here moving, you would expect from theory, right, that sigma 1 would be there at about maybe 30 degrees from the fault, right? So this would be conjugate faults. So that's what you'd expect. And sigma 3 would be over here. What's observed, now I need two colors, but I only have one today. What's observed is sigma 1 is like that, almost perpendicular to the fault. So the angle here is like 5 degrees, 10 degrees. Now what is that? Similarly, low angle normal faults. Anderson's theory of faulting suggests sigma 1 should be vertical, and you should have 60-degree dipping faults. Many places in the world, we'll see examples, where normal faults may be like that. Might have a dip of 5 degrees. Now, why is that a paradox? Draw the dreaded Moore diagram and think about that geometry. In either one of those particular cases, I'll just draw the Moore circle, sigma 1, sigma 3. Let's do this one's easiest. Sigma 3 is over here, right? So the normal to this plane, if that's 5 degrees, the normal to this plane, not well drawn, is 5 degrees, right? So if I put that on the Moore circle, 5 times 2 is 10. That still only gets me here. That's the low angle normal fault. Why would it ever move on that surface? Right? Because friction line's here, or the braking line is there. That's so far off that line.
Does it have to do with the original creation of the fault itself? And
well, we'll come back to that and talk about normal faults. Now, I'll give you two explanations. One of them is the friction's wrong, related to what you said, that the real world is such that something in faults drops the friction so that it can move on a lower angle fault. The other hypothesis is that this isn't original. That's rotating. That doesn't help with this one. But we'll talk about that when we talk about faults. But that's a bigger paradox. That one's real, and that one remains. Next time we'll talk about ductile.